to our next session. So this is a continuation of our discussion about um, beam columns, wherein we first discuss the interaction equation, and then right now we will be continuing that topic and focusing on the effect of that interaction equation in our frame. Okay, so for today we will be discussing the moment amplification method, focusing on brace frame. Okay, so as a recall, so we have discussed again yung tinatawag natin interaction equation, and our interaction equation is given by the formula. Our required strength over available strength should be less than or equal to unity. So this interaction equation actually is being used na before pa when we were calculating for the efficiency of our section. So the required strength pertains to the applied loadings that our members need to withstand, and the available strength is the capacity of our members depending on whatever section it is assigned with, so again, the ratio should be less than or equal to unity. And then we discussed that when beam column action arises in our member, we need to determine between these two the equation, the interaction equation to use. No? That's why we are checking the ratio of the compression strength, whether it is greater than or equal to zero point 0.2 or less than that value. If it is greater than or equal to 2, we say that it possesses larger axial load. So it means that we try to reduce yung moment, yung bending strength natin, or flexural strength natin by almost 1/10 of the capacity, or 8/9. And then we check whether the performance of the compressive force and the moment or the bending strength is less than or equal to unity. When the ratio of our compression strength is greater than 0.2, we say that it has smaller axial load. Okay? When this happens, yung compression term natin is being halves, and then full natin ginagamit or utilize yung bending strength natin. Okay? So when this equation is satisfied, we suggest that the section is adequate to support the given loading, whether it performs as a beam or as a column in our frame. And then since we are calculating for the compressive strength of our section, so we are using the equations from the AISC or NSCP for compressive strength. And then we also utilizing the LTB capacities depending on which zone our section lies, depending on the lateral torsional buckling that we have. And then this is our limiting values for our LP and LR. And then we solve an example last time. Okay. So today we will be focusing on methods of analysis for the required strength. Again, for our equation, the required strength is the numerator. Okay. So required strength natin over yung ating capacity, yung allowable strength natin should be less than or equal to unity. Pero in some cases, the required strength or the loadings from our loadings. So for yung way of calculation that we are doing, it is considered as a first order analysis. So we are not discussing or considering the effect of possible movement of our section or our member when it is subjected to loadings. We do not consider any other effects that may happen in our member. We just account we just analyze it as is based from the theory of structures that we know. Okay, but for the this particular section, the interaction equation that we have identified is satisfactory so long as the actual load is not too large. Otherwise, if it becomes too large, okay, what happens is uh, it it produces secondary movements or additional movements dun sa section natin sa member natin, which causes additional deflection over dun sa ating section. Okay, so let us consider this member. Okay, let's say we consider yung point O. When that point, so let's say ito yung section na yun, then this is point O, we cut that section there. We know that when we cut our section, okay, this is our support reactions, okay, and then from our cut section, we know that the elastic curve natin, so ito yun yung deflection curve natin, is ganun yung itsura niya. Okay, so ito yung elastic curve natin. Okay, and at that point, we know our section is possessing a deflection already. Okay, based from um, the transverse loading that our section is subjected to. Okay, so sa point O natin, so ito din yun, same point. This is the same point as point O. We know that from that section, once we cut it, may expose yung kanyang mga internal forces. Okay, so kung ganito yung direction, so we have an axial or a shear force. Okay, and then we also have an axial force, and of course, since this um, axial force produces a moment papunta dun sa original na position ng ating beam, so that moment is actually the secondary moment that we need to account for. Okay, so yung sa secondary moment, so kung this is P, this is also P, and then let's say yung deflection natin is phi, so this moment is actually equals to P times Y. So it means that besides from the actual loading that we have from our section, our uh, member is also being stressed by additional moment caused by the actual load with or multiplied by a deformation y at that section. And we know na kapag ganito yung itsura ng member natin, the maximum deflection it has is at the center. And kapag ganyan yung nangyari, we exhibit yung tinatawag natin P delta na moment or additional moment doon sa ating section. So P delta or P small delta is being observed when our section is localized. Ano, ba, titingnan natin yung local member natin. Okay? So, these are called secondary moments. So, in addition to the secondary moments caused by the member deformation, so sabi natin, yun nga, yung mismong P small delta natin. Additional secondary moments are present kapag yung isang end natin, kasi do sa condition natin at first, we restrained yung ating connection dito at its end. So we assume that it cannot move. If that is the condition, we prevent sidesway or sidesway prevented. So ibig parang braced yung mismong column natin in all directions. Hindi siya pwedeng gumalaw. So, if that is the case, ang may experience lang nung column natin, ng member natin, is yung P small delta. Yun yung secondary niya. Now, once we have an unbraced frame, okay, unbraced, ibig sabihin the one end of our member is free to translate with respect to the other. So, pwede siyang mag-move So yung movement caused from the original position dito, no? Pupunta do sa new position niya. That is the global deformation that our frame exhibits. So we also consider that because this axial loading na P causes an additional moment papunta dito sa member natin, which is a tinatawag natin P big delta. P big delta effect. Okay? So for braced frame, meron tayong P small delta lang. Pero once we are talking about unbraced frame, we are considering both P small delta because of the this particular deformation from the original, and then yung curvature natin, and then additional moment natin or uh, movement caused by the change in position of the other end of our member, which is a P's big delta effect. Okay. So for all but simplest structures, a computerized frame analysis is required to obtain yung mga bending moments and axial loads natin for our member. So the analysis for the required strength should account these effects. So kailangan kapag nag-displace or nag-move yung geometry ng member natin, yung member out of plumbness. So ibig sabihin, we consider that our section, let's say our column, once it is being erected, it is not 100% na naka-straight, ano? Sometimes um, it exhibits some distance from the center line or from the vertical line. So that is sometimes considered in the design, and of course yung inelasticity natin. So we have three approaches to determine yung required strength considering these effects in our member. We have the direct analysis method, the effective length method, and the first order analysis. So earlier, I have mentioned already that so far, we are just doing first order methods wherein yung analysis natin do not take into consideration yung displaced geometry natin. Okay, so we are just using the value of the ultimate moment that we calculated based on structural analysis, and then that's it, ano? Pero in reality, we have observed that um, that is not the case when it comes to real life structures, because we exhibit secondary effects or secondary moments from the deformation or the offset nung deform shape natin from its original shape, which is caused by the eccentric loading natin from the center ng member natin, which is caused by the P delta, small delta, and P big delta. Okay. And then we have yung mga so-called second order methods. When we say second order, analysis that accounts for all effects needed to calculate yung required strength. So yung all effects being discussed here are these effects. So kino-consider niya lahat yung consideration niya. Okay? So what are the differences of these three methods? So first, for the direct analysis method, that is a second order analysis that considers both the P delta, small delta, and P big delta effects. Meaning, we are considering, pag sinabing ganito yung case niya, we are considering braced frames, unbraced frames. Okay, so we are assuming that one end of our member is free to translate relative to the other. Okay, so kaya nga unbraced. Okay, this approach uses an amplified first order moment. Okay, so ibig sabihin yung moment value that we have identified from the structural analysis, minumultiply natin by a certain factor, ina-amplify natin, and also its axial load. So member stiffness are reduced. So yung pag sinabing member stiffness, that is our inertia, nire-reduce natin yung inertia or yung flexural rigidity natin. And then the effective length factor of K is equals to 1. So laging equals to 1 yung factor natin for our length. That is for the direct analysis method. next we have yung effective length method. So sa effective length method, is second order analysis din siya, or tinatawag na approximate second order analysis, where in yung effective length factor K natin must be determined. Ano? The method for determining yung value of the effective length factor is based on the support condition that we discussed using the table that we used during the compression analysis of compression members, and also the one being used once we are considering frames, the alignment charts for the value of K. And then if we are also using effective length method, we see here that the member stiffnesses are not reduced. So, ibig sabihin yung kanyang flexural rigidity, so tinatawag nating EI, okay, flexural rigidity, hindi natin binabawasan yung capacity niya. So, as is na buong-buo yung value niya. Okay? Unlike kay direct analysis method na nire-reduce natin yung stiffness niya. Okay? And then we have first order analysis method wherein this is a simplified version of the direct analysis method. So, first order analysis method is a second order method pero simplified version lang. Okay? That can be used certain conditions are satisfied. Okay? So, we will not be discussing these three methods in full detail because this is not part of the course. Pero if you want to study these individual methods, the AISC construction manual has an explanation for that under Appendix 7 and 8, if you will check it. And then there is a discussion how to use these methods in a particular example. Okay? So, under first order analysis method, yung member stiffnesses natin are not reduced, so katulad ng effective length method. And ang ginagamit na effective length factor is always equals to 1. So, ang assumption niya, always nakapin-pin condition yung ano natin, yung mismong support condition natin. Okay? So, hindi nireduce yung stiffness, then K is equals to 1. So, yun yung kaibahan niya, no? K is equals to 1. Pero yung member stiffnesses niya, nire-reduce kapag direct analysis. Kapag first order, hindi siya nare-reduce. Retain lang siya katulad nung sa effective length method natin. Okay? So, between those three, the direct analysis method daw is the preferred method. So, if the appropriate software is available, kasi pag what's na we model our structure in a computer software, it can perform second order analysis na. So to identify the value of the moment and the actual forces. No? Pero if second order analysis is not available, meaning the available software, ang sabi ni code, we can use the moment amplification method to uh, to use as a substitute for the second order analysis. So even without a software, we can calculate for at least for the approximate value of the actual applied moment in our section. Okay, so in the diagram, let's say we have a member, a column subjected to an actual force and a moment, M. Ano? So looking at the diagram, when we look at the value of M, okay, the moment diagram produces a curve like this one, ano? So based from the curvature of the applied moment. So we see that it can be visualized as this line that is from the first order. But due to this moment, when we again cut a section, and then when we visualize the cut section, say this is the cut section, then from this cut section, we have a distance. Okay, this is our distance, and then this is our P. Okay, this P, or the presence of this couple with distance of delta, small delta, produces moment going towards our section. That is the second order effects. That's why from our first initial moment or deflected shape, the second order effect um, will be additive with our first order. So pag tingnan natin yung moment diagram niya, nung nag-calculate lang tayo as is uniform lang siya all throughout the member. But once we consider the secondary effects, we see that at certain location, the value of the second order moment is being added to the uniform first order moments, and we see that as um, the distance is going towards the center, we see that that is the location where the maximum value of our moment uh, is located. No, same with the uh, deflected shape. Natin dun yung highest deflection natin at that position. Okay, so this is the P delta effect for beam column with uniform bending. So the moment amplification method entails computing the maximum bending moment resulting from flexural loading. So ibig sabihin from our transverse loading, we calculate for the moment by first order analysis. Ano? So after that, we multiply it by a moment amplification factor. Okay, so this moment amplification factor can be derived using this diagram. Okay, so same idea siya of this one. Yung effect natin, yung first order natin, ito yung deflected shape, ito yung kanyang moment diagram. Pero since meron tayong additional moment caused by the eccentric loading, we produce another deflected shape and also moment that is included in our calculation. Then we see that this is the diagram to derive the amplification factor that we need for our first order moment. So let's say the beam that we have has as a crooked straightness, no? So di siya actually perfectly straight. So in but first, meron na siyang when the moment of the beam is analyzed, meron siyang eccentricity o yung loading natin has eccentricity from the center. So, yung deflected shape natin is this one. And as you can see, it has yung deflection natin is at center. So, yung deflection na yan will be total of the eccentricity from the center line of our beam plus the deflection at the center. So, upon deriving it, we have this value for the maximum moment is equals to P multiplied by the eccentricity plus E over PE over P minus 1. Pero we can actually reduce this equation. Okay, so this M max. Okay, so P multiplied by E. Okay, so that is E plus E over PE over P minus 1. So when we factor out yung E, so we can um, uh, factor it out. So 1 plus E over PE over P minus 1. Then simplify. So this is P over P minus 1. So this is PE over P minus 1. This is no longer E. This is 1 na to. Okay. Plus 1. and then this will be 0. So we have PE. So that is PE over P over PE over P minus 1. And we can manipulate this one as P over PE over P over PE. So this will be 1 na lang to. And then this will be PE. This is 1 over 1 minus P over PE. Okay, that is for a maximum moment. So when we let PE as our uh, first order moment, okay, so we have the maximum moment is equals to M sub O multiplied by a factor 1 over 1 minus P over PE. Okay, wherein yung P is our since we are considering the maximum moment, so this can be yung PU natin for LRFD or PA. And then P sub E is actually our uh, Euler's Macklin load considering yung moment natin at the strong axis natin. Okay? So, meaning the amplification factor is this one. This is our amplification factor. So, amplification factor is equals to 1 over 1 minus B over B sub B. Okay. So, that is the factor that we need to account for the secondary effects of our uh, moments. Ano? So once multiplied natin yun sa calculated natin moment from our first order analysis, we have now our maximum moment due to the second order na. Okay? So that's it. So let's try that into an example. So compute the LRD amplification factor for the beam column example of the foregoing lecture. So yung previous problem natin. So our previous problem, we had this problem. Okay, let's look at the notes last time. So this is what we had. Okay. So this was our problem, and we are trying to calculate for the interaction equation of this one. No? Pero ngayon, we try to identify how much is the amplification factor needed for our required moment. So, ibig sabihin, from our required moment na MU, ilan yung amplification factor dapat na i-apply natin sa kanya once na na-identify natin yung mga needed values natin. Okay? So, from that problem, so dito, we intend to get the value of our maximum moment equals dun sa first order natin na moment multiplied by yung amplification factor natin na 1 over 1 minus PU over PE. Okay? So, given that problem, we have a W10 by 49. Okay? So, that is a W10 by 49. And from that problem, we have a PU equals to 1.2 PT, 1.6 PL. So that is this one, 200.4 kip. Okay, so we have a value of 200.4 kip. That is for our PU. Okay, so ibig sabihin, yung value that we need is already dito sa equation natin. Okay na tayo dito sa PU. Okay. The next value that we need is the value of P sub E. Okay, so P sub E. So P sub E. So equation natin for P sub E, of course, is pi squared E over KL over R squared. Okay? Pero, since we are pertaining dun sa beam natin, and dun tayo sa moment about dun sa strong axis niya. Okay? So, yung column natin is, ito yung itsura ng column natin. Okay? So, from this example, ito, no? Ayan, yung column natin. So, yung section natin is ganito yung itsura. Kailangan natin is about siya dito, no? Sa ano natin. So, ang kailangan value natin ng R for the slenderness ratio is Rx tayo. Okay? So, we need pi squared. Key natin is 29,000 ASI over yung K value natin since that is a pin-pin connection, it is 1.0 times yung length na ginamit natin is yung 17, of course. Tapos times natin 12 to make it in inches. All over yung Rx natin. So, Rx makukuha natin sa table 1-1. So, W shape. So, let's look at W 10 by 49. So, ito yun. W 10 by 49. Rx is 4.35. Okay. So, 4.35. So, dito, that will be 4.35 inches. And this is squared. Cancel, no? So, so since this is PE, we need to multiply it. Itong formula ang nilagay natin is naka-FCR pa lang to, no? So, ito pa lang yung, ano natin, yung stress natin, FE. So, para maging loading, times pa natin ng 8G. Okay? So, multiply natin ng 8G. KG natin based from table 1-1. Ang AG natin is 14.4. Okay? So, 14.4 times 14.4 inches squared. So, titira is in kip. So, that is squared 29,000 times 14.4 divided by 70 times 12 over 4.35 then squared. That is 1874.038 kips. Okay. So, ito na yung PE natin. So, okay na tayo sa PE. So, according to the calculation that we had, ano yung maximum moment natin dun sa section? Maximum moment natin was taken as ito, no? Based from yung QU natin and then getting the value of the maximum moment dito sa structural analysis natin, we have MU is 107.1 cubic feet. So, yun yung ating M sub O. 107.1 cubic feet. So, using yung Mmax natin, i-amplify na natin ngayon. That is MO multiplied by 1 over 1 minus P over P. So, that is 107.1 1 over 1 minus P natin is 200.4 over P sub is 1874.038. Mmax natin is 107.1 1 over 1 minus 200.4 over 1874.038. That is 119.924 kip. So, ito yung gagamitin natin ngayon. Mmax na isa-substitute sa interaction equation natin. So, this should be the new MU para dun sa equation natin na interaction equation. So if you want to kung how much yung in-increase, you just evaluate itong function natin na to. So alisin natin yung multiplier na 107.1. Makukuha natin na yung amplification factor natin is equal sa 1.120. Okay? So it means amplify na 12% yung mismo section natin. Tayo 12% increase in yung so percents of secondary effect sa section natin. Kulang pa ng 12% pala yung niretain natin before, no? So dito, based dito. So yung MU natin dito is 107.1 lang. Ginamit natin dito sa uh, dito. Okay. Para makuha yung sa MUX. So dapat multiply pa natin ito ng 1.12. And then before makuha natin itong value dito. Then saka natin makukuha yung interaction equation. So that is how you calculate for the amplification factor. Okay, next. So there are two types of secondary moment as we have already mentioned earlier. We have yung P small delta and P big delta. So si P small delta, okay, is caused by the member deflection. So pag P small delta, local member to, no? Localize siya. Yung mismong ano lang, yung mismong column lang yung pinag-usapan natin. But when we talk about P big delta, this caused by the effect of sway, and the member is part of an unbraced frame. So global na to, no? Globalized. So yung overall movement na niya based dun sa mga iba pang members present dun sa structure natin. Okay? So since we have two types of secondary movements, it is imperative na dapat may dalawang amplification factor tayo based on the secondary moments that we have. Okay? Kaya we have two amplification factor present. We have B1 and B2, where it's si B1 is para dun sa P small delta natin, and si B2 para siya dun sa P big delta natin. So, ibig sabihin, if these two delta F, secondary moments are present, kailangan kunin natin yung value ng B1 and B2. And ano yung sabi natin kanina? Earlier, we mentioned na kapag braced frame siya, okay, wala tayong movement dun sa other end ng member natin. So, ibig sabihin, may eliminate na si B2. Okay? B1 lang yung present. Like kapag unbraced tayo, pag unbraced yung section natin, yung frame natin, kailangan niya magka meron ng B1 and B2 kasi present parehas yung secondary effects natin, which is yung P small delta and P big delta. Okay? So, the amplified moment to be used in the design is computed from the loads and moments as follows. So, yung required moment natin ngayon, hindi na lang siya basta MU na galing to sa load combination natin. It will be a combination of B1 times MNT plus B2 times MLT. So, anong kakaiba ng dalawa? Again, si B1, sa amplification factor, kapag siya ay braced, no? So, ibig sabihin, kapag braced yung system natin, may B1 tayo. So, this is from, again, galing yan sa P small delta effect. Okay? Now we have B2, that is from the P big delta effect. Okay? So, ano may MNT? Si MNT is maximum moment assuming that there is no sideway occurs. Okay? No sideway, ibig sabihin naka-brace siya. Kaya nakalagay niya NT, ibig sabihin no translation. Walang movement. naka-fix lang siya, naka-steady lang siya. Okay? And sabi natin kapag di ba pag naka-brace tayo, bawa parehas siyang nakapin dito, hindi siya pwedeng mag-move. Nagkakameron na siyang deflection na ganyan. Pero hindi siya pwedeng mag-move. Unlike kay MLT, okay, maximum moment caused by side wave, kung bawa ito yung member mo, tapos please siya to move, nagiging ganun siya. No? Ayan. Pwede maging ganyan yung section natin. Okay? So, yung LT naman meaning, meron siyang lateral translation. May movement siya sideways. No? Kaya nakalagay, caused by sideways direction. Okay? Kaya pag sinabing naka-brace yung frame natin, MLT natin ay 0. So, ibig sabihin, for braced frame, ito yung binabanggit ko kanina, no? For braced frame, so, MLT is equals to 0. Or, dahil wala nga tayong P delta, P big delta effect, wala tayong B2. So, wala tong term to. So, yung MR natin for braced frame is actually B1 lang times yung MNT natin. Okay? And then kapag unbraced siya, so pag unbraced, present yung dalawa. So we have to calculate for it. Okay? Kaya we need to discuss them separately. Ano si braced frame tsaka si unbraced frame. So for this session, we will just focus first on the braced frame tayo. Okay? So but before that, kung yung um, bending effect natin is na-amplify, of course, our uh, actual strength should also be amplified. Ano? So in addition to the required moment strength, the required actual strength must be accounted for secondary effects also. So the required actual strength is affected by yung displace ng geometry ng structure natin during loading. But this is not an issue kapag P small delta pinag-uusapan natin kasi sabi natin hindi siya pwedeng mag-move. So wala siyang displacement, walang displacement yung geometry yung section natin. Unlike kapag uh, big delta tayo, may joint displacement tayo. Kaya mangyayari sa equation natin, wala tayong amplification for the no translation no part, pero dun sa may lateral translation, meron tayong factor sa kanya, B2, which will be discussed later on. But first, we focus lang sa brace frame now, members in brace frame. Okay? So, for members in brace frame, the amplification factor daw, it was derived for members braced against sideway. Okay? So, for members whose ends cannot translate with respect to each other. Okay? Brace against sideway. So, hindi nga siya pwedeng kumala. When a member is subjected to equal end moments, so pareha siya ng value ng moment, bending is a single curvature bending. Pag sinabi kasing single curvature yung bending natin, it means that our section only has one direction natin, movement natin. So, it's like saying yung section or our section itself um, has moments na katulad nito, no? Na nagkakos halimbawa ng one direction of the curvature only. Ito. So, the maximum moment amplification daw, when this happens, is occurring at the center where the deflection is largest. So, katulad nito, since yung movement natin is towards the center, nagkakos siya ng gantong deflected shape, and as you can see, the maximum deflection is at the center. Okay? So, for equal end moments, yung moment is constant throughout yung length ng member. So, the maximum primary moment occurs at the center. Okay? Thus, the secondary moment and primary moments are additive. Katulad nga nito. Yung secondary moment natin is caused by P small delta. And the primary moment is taken or analyzed using our equation from sectional analysis. So, para makuha yung total moment ng problem, again, we add those two values para makuha natin yung required moment that we need to resist. So there's a note here na even if the end moments are not equal, so ibig sabihin, may pwede mas malaki yung nasa applied sa taas compared dun sa applied at the bottom. As long as they differ in direction, there will be single curvature bending, and the maximum primary and secondary moments will occur right next to each other. Okay? So, yun yung pag single curvature siya. Ngayon, what does it mean kapag ano siya, no? Um, pag, pag hindi na siya single curvature. So again, pag single curvature, um, pwedeng one is clockwise, katulad nito, one is clockwise, and the other one is counterclockwise. So there will be always single curvature kapag ganun yung case. Okay? Ngayon kapag halimbawa para siya naging counterclockwise. Okay? So if the applied end moments produce reverse curvature bending. So kapag may reverse curvature bending, meron tayong double curvature katulad nito. Meron siyang uh, counterclockwise sa ganito counterclockwise din. So you can see on the deformation diagram natin, deflection shape natin, it is in an S shape, ano? So it means that yung one end natin is bending on a different direction than the other end. Kaya nagkakameron siya ng S shape. Okay? So, when structure bends in two opposite direction, nagpo-form siya ng S shape. Katulad nga nito. Okay? So, tawag natin reverse curvature bending or double curvature bending. So, the maximum primary moment, ang bawat dito, yung maximum primary natin is ito, is at one end and the maximum moment amplification of course between the ends. So, yung amplification natin na maximum, yan ano, pwedeng dito or ito. Okay. So, hindi na siya nag-occur doon sa same part, ano, yung maximum niya is nandito sa part na to. And then, ito yung maximum na dito. So, pag in-add natin siya, pwede ganito yung itsura niya, maximum niya, or ganito yung itsura niya. Mas greater than shown sa M2 natin, of course. No? Okay. So, this is our secondary effect. So, depending on the value of the actual load, the amplified moment can be either larger, smaller than the end moments. Okay. So, the maximum moment in a beam column, therefore, depends daw on the distribution ng bending moment within the member, of course. No? So, it depends on the distribution ng moment along the member. Okay? So, this distribution is accounted for by factor C sub M, tawag, ano? Applied to the amplification factor. So, our original amplification factor again is 1 over 1 minus um, P sub R, okay, o over P sub E natin, okay, and yung para i-account yung um, tinatawag nating distribution ng bending moment, ano, within the member, may factor ngayon siyang CM, pinumultiply na CM, which is, yan. Tapos, dito um, sa mismong strength ng ating actual strength, not the compressive strength, we multiply a factor alpha depending on the design philosophy that we are using. So the required unamplified actual stress natin, the PNT plus PLT. And then, itong factor natin, 1.04 LRFD, then 1.6 for ASD. Yung PE1 is Euler buckling load using this formula. Wherein yung formula is pi squared, tapos yung modulus of yung fractional rigidity natin, E times I, over the length natin squared. Okay? So, since dito, nakalagay, EI is a reduced fractional rigidity, ang value niya is 0.8 tau B EI. So, si tau B, ito yung kinakalculate natin before when calculating for the value of the effective length for frames using alignment chart. Pero may note sa code, ano? Under certain conditions, yung tau B natin may be equal to 1. And the effective length in first order method, di ba sabi natin sa effective length sa first order method, yung ating fractional rigidity is unreduced. So yung ating um, inertia is unreduced, katulad ng binabanggit dito, no? Sa effective length method, member stiffnesses are not reduced. Sa first order, member stiffnesses are not reduced. So, yun yung gusto sabihin niya dito sa statement na yun. Then the moment of inertia I and effective length LCI are of the act of are for the axis of bending. So kung saan nagbe-bend, kung saan yung about, moment about a certain axis applied yung forces natin, yun yung consider natin inertia. So for this case, usually is about sa strong axis natin. So usually IX ang ginamit natin. Okay? That is around the plane of bending. So in evaluating the value of C sub M, uh, it only applies to brace condition lang. Okay? So, ibig sabihin, kung unbraced yung frame mo, we don't need to calculate the value of CM na i-multiply natin dito sa mismong ano natin. Ito yung amplification factor natin. Hindi natin mo multiply sa CM. Okay? So there are two categories for members. Those with transverse loads applied between the ends and those with no transverse load. Okay? So ang ibig sabihin, pag there are no transverse load, so nabawa ito yung section mo, okay? Ano ka axial force, ano ka libawang moment, okay? Pag no transverse load, wala kang naka-apply dito na transverse dun sa member natin. Okay? Unlike halimbawa, you have transverse load, yung section natin. Then, those with applied transverse load, so pwedeng yan, may uniformly distributed load siya dito. Okay, so those with transverse load applied between the ends, so ito yun. Those with no transverse load. So, ito yung sa kabila. Okay, so if there are no transverse load, so itong first condition natin, ang CM daw is taken as 0.6 minus 0.4 plus ratio ng M1 over M2. So M1 and M2, M1 is the end moment that is smaller in absolute value and M2 is the larger end moment. So, ayan. So, kailangan i-check kung anong type ng curvature meron. If we are single curvature only, it means na magkaiba yung direction ng ating moments. If the other end is counterclockwise, clockwise naman yung isa. Okay? Or pwede clockwise first, then counterclockwise. It shows a single curvature bending. Ang sabi, gagamitin natin is a negative ratio. Negative M1, M2 natin. Whichever is smaller, yun yung M1, M2 yung larger. And kapag double curvature tayo or reverse curvature tayo, pagparas ng direction, ano, ibig sabihin, positive naman yung ratio natin. Okay? So, just need to use a positive or negative value. X. For number 2, for transversely loaded members, so ibig sabihin, yung ating section niya is nagkameron na siya ng, ng transverse loading. So this is our column. Then we have our loading dito. Yan, may transverse loading na yung column natin. So CM can be taken as 1.0, sabi daw ni code. Pero a more refined procedure for transversely loaded members is provided using the formula in table C8-1. So, galing sa AISC construction manual. So, ito yung formula niya. 1 plus psi times alpha PR over PE sub 1. So, ito wala tayong problema dito. That is the same formulation dun sa previous slide natin. Si psi lang yung nagbago at si psi will depend dito sa table natin. So, depending on the condition of our table. So, halimbawa, like this one. So, halimbawa dito, ang section natin is may moment siya, may axial, tapos may shear siya dito. So, pwedeng ito yung condition natin. Okay? So, -4 yung side. I-substitute yung value dito. And then, this will be the formula of CM. So, nilagay na niya yung psi value ng -0.4, no? So, ito na, pwedeng dito ko na lang tumingin mismo sa value of CM. Okay? Pero you can use CM equals to 1.0 for simplicity. Okay? So, to use this concept, let us have an example problem. So, we have this problem, pero bear in mind what is our goal ba of solving these problems. No? The goal is to check whether our section or our white flange is capable of withstanding our applied forces, whether it behaves as a beam or a column or as a beam column. Kaya, ang end goal natin is to check for the interaction equation pa din based from our first discussion. Okay? So, we have here the member shown is a part of a braced frame. So, that is a first clue agad natin, ano? Part siya ng braced frame. Okay? And again, pag braced frame, pinag-uusapan natin, wala tayo P big delta, no? P small delta lang tayo. So, ibig sabihin doon sa formula natin na nakita kanina for MR, okay, for MR, so, pwedeng alisin na agad natin itong term na to kasi ito lang yung magiging equation natin for MR natin. Okay? So, B1. So, pwede natin ilagay dito para balikan natin mamaya. MR is equals to B1 MN. Okay? 0 na yung sa P delta, yung second term. Okay? The service loads are as shown and the bending is about the strong axis. Ano? So, strong axis tayo bending. So, ibig sabihin, yung inertia natin is Ix. Yung R natin is X din kapag kukunin natin yung Euler's backplane load sa plane ng bending natin later. Okay? An analysis consistent with effective length method was performed. Ibig sabihin na, sa effective length method, sabi natin kanina, sa effective length method na approach, we assume na yung effective length factor must be determined or the member stiffnesses are not reduced. No? So, EI natin is buo and then yung K natin must be determined. Okay? Pero in this case, I think it was given na the flexural rigidity, EI, is unreduced, so buong-buo siya. A572 grade 50 is used and the member is adequate. Is the member adequate? Ano? Ito, KXL, KAYL is equals to L. So, ibig sabihin, in both direction, K value is equals to 1. So, binanggit na din dito. So, hindi natin kailangan mag-analyze ng value ng K. Okay? Right. So, what do we need to do first? Ano? So, to start the calculation for this problem, first is we need to identify yung ratio natin for the interaction equation. We need to determine what equation, yung may reduction ba yung moment o yung may reduction um, yung axial load, no? So, we intend to get muna si PR over PC kung ano yung magiging value niya. Okay? So, let's calculate muna si PR over PC. Okay? So, PR over PC. So, di ba si PR, alam natin equal siya sa PU. Okay? So, based on our formulation, that is 1.2 PD plus 1.6 PL. So, that is 1.2 nung 70 plus, sulat natin ano, plus 1.6 nung 210. That is 420 kip. Next is yung PC natin. Okay? PC is equals to sa VPN natin. Okay? And VPN is based dun sa compressive natin, no? So, pag ginagawa natin para makuha si VPN, letter A, kinukuha natin yung largest na KL over Y. No? So, yung slenderness ratio. Since ang value natin is the same both directions, si RY yung mag-govern. So, that's 1.0 times 14 times 12 over yung RY natin, which is, check natin, 12 by 65 yung section natin, ano? So, lagay natin yung RY niya. 12 by 65. So, looking at this diagram, so 12 by 65. So, yun yung pinaka-last. So, let's highlight lang. So, kailangan natin RY. So, RY, so ito, 3.02. Okay, 3.02 inch. So, KL over R, this one, 14 times 12 over 3.02. That is 55.629. Okay, so once we have that, we can calculate now yung value ng ating FE, which is pi squared E over KL over R squared. So substituting na lang the value. Pi squared, 29,000 over answer squared, that is 92.490 KSI. Then, para makuha si FCR, so KL over R natin, 629, compare with 4.71 squared of E over Fy, which is less than siya kasi this is 113 point something. So, if that is less than, so tayo ay not slender, o intermediate lang yung point natin. So, FCR equals to 0.658 Fy, FCR, Fe multiplied by Fy. So, FCR 0.658 raised to 50 over yung Fe natin times 50. We have 39.875 KSI. Okay? Then once we have FCR, we can now get yung value ng PPN. PPN is 0.9 FCR times AG. Okay, so FCR natin 0.9, 39.875 KSI. AG natin, looking at the table, that is 19.1. So 19.1 inches squared. So VPN is equals to 0.9 times 39.875, 19.1. That is 685.451 kip. Okay, so PU over VPN now will be 420 over 685.451. That is 420, 685.451. So 0.613. Okay, so that is the value. That is greater than 0.2. Okay, so ibig sabihin larger actual load. So ang re-reduce natin is yung moment natin. So ang PU, so gawin natin PR over BC plus 8 over 9. And then that is MRX, MCX. And then wala na tayong Y, ano? Nalagay lang natin kasi ika-cancel na lang natin. Should be less than or equal to 1.0. Ito, alisin natin. So, ito lang yung kailangan natin i-satisfy. MRX over CX. Yan. Ito yung kailangan natin satisfy. Ano? Natin ang kulay blue. Okay. Yan yung gusto natin satisfy. So si column part, okay na tayo kay column part. May value na tayo. Ang una natin ngayon ay si beam part. Okay? So for the beam, we need to calculate MRX and MCX. Okay? So dito, si MRX, so sabi natin kanina, yan, binilugan natin. Brace frame tayo. So yung MR natin in X, B1 MNT lang tayo. Okay? So that is B1 times MNT. Okay? Balikan natin yung meaning ng MNT. Okay, so based dun sa MNT is the maximum moment, assuming that is no sideways support. So maximum moment. Okay? Ay yung diagram natin. Okay? May applied moment siya at ends. Ano? Meron siya dito clockwise tsaka counterclockwise. So since magkaiba silang direction, we can assume na we have a single curvature. Okay? Kung single yung curvature natin, we also know na yung kanyang moment diagram is hindi uniform ano, kasi magkaiba ng value. So, possible ito yung itsura ng moment diagram natin. So, meron siyang sariling value dito, meron siyang sariling value. So, kunin lang natin yung kanyang um, value using yung ating load combination. So, 1.2 ng 11 plus 1.6 ng 36, that is 70.8 if it. And then 1.2, 14 plus 1.6 ng 41, we have 82.4 if it. Okay? So si MNT is maximum. So 82.4 yung gagamitin natin for MNT. Okay? So for MNT, alam na natin na 82.4 yung i-fit natin. Ngayon si B1 yung kailangan natin. Okay? For B1, so since ano tayo, alamin natin kung anong condition ni B1 ngayon. Meron ba siya transverse load o wala? Okay? So, yung given natin, if you look at the given, okay? Ito yung column natin. May shear siya dito, pero wala siyang transverse loading along dun sa length niya. No? So, it means dun tayo sa una papasok. Okay? So, ang formula ni B1, tignan natin dito. B1, ang formula niya is ito. Okay? So, let's copy this. Okay. So, for B1, yan yung formula kailangan natin for B1. So, kailangan natin si CM. Pero, again, ito yung beam natin, yung column natin. May apply siya ditong moment. May apply siya ditong moment. So, ibig sabihin, single curvature tayo. Okay? If that is the case, yung value nito is yung 70.8, if I'm not mistaken. M2 is 82 point. Okay? So, for CM, dun tayo sa no transverse loading. So, ito yung gagamitin natin formula for CM. So, CM So Cm is equals to 0.6 minus 0.4. Pero since single curvature siya, again, pag single curvature, sabi natin, that is what type of moment? We have a negative ratio ng M1, M2. Okay, ito. Negative yung M1, M2 natin. So, dito sa solution natin, it should be negative yung ratio natin. So, 70.8 over 82.4. Okay, so Cm is equals to 0.6 minus 0.4 minus 70.8, 82.4. That is 0.949437. Okay. Then yung Cm natin is okay na tayo dito sa Cm dito. Next is yung alpha. Alpha is 1.0 for LRFT. Okay na tayo dyan. PR. Okay. So, PR natin ang gagamitin is the one we calculated, ano, which is yung 420. So, PR, yun yung PU natin. That is 120, 420 rather. Okay. Okay. So, ang wala pa natin is si PE1. Na-base siya sa Euler's backlink equation, and then EI, E, E times A over KL over RX tayo. Okay? Naka-X siya. Kasi yung kaninang na-calculate natin, due siya sa um, compression, kaya RY tayo kasi maliit. Mas maliit yung value ng RY sa weak axis over time. Kaya ito yung value ng KL over R. Pero since dito, bending tayo about sa plane of bending, KL over X na tayo. Okay? So, upon substituting value, I squared, E natin is 29,000, area natin is 19.1 over, K natin is 1, ang length natin is 14. 14 times 12 over Rx natin. So Rx is 5.28. 5.28 and then squared value is 5399.83. Yep. Okay. So, copy ko lang yung values na to. Then we'll proceed to the next page. So, we have now B1 equals to Cm all over 1 minus alpha PR over PE1 should be greater than 1. So that is 0.9437. 1 minus 1. PR is 420 all over yung 539.9834. 0.9437, 1 minus 1, 420 all over 5.